today we're going to look at rate laws and how we determine the order of a reaction or the order of individual reactants. Now, the order is that M and N we were talking about in a general rate expression. For instance, if we had something like this, rate is equal to K, A to the M, B to the N, the order of the reactants are these superscripts right here, and they tell us about what will happen to the rate if we change the concentration of those particular reactants. Those numbers in the AP world will usually be either a 0, a 1, or a 2. Those are the only ones that we've ever had to calculate. So what does it mean if it's 0 order? 0 order means that when we change the concentration of the reactant, there is 0 effect, no effect on the rate. It's not very common, but it does occasionally happen. The way that this would look if you saw a reactant that was 0 order, they might actually put it in like this and say that rate was equal to K times that reactant concentration raised to the 0 power. But remember, if any number raised to the 0 power is 1, so you could possibly see it simply as rate is equal to K. So 0 order means 0 effect on the rate. So what happens if you see in a particular rate law that one of the reactants has a superscript of a 1? And remember, since any number raised to the first power is itself, you might also see it as simply that concentration with no superscript. What that means is that if you change the concentration of the reactant, you're going to change the rate by that same factor. So if you double the concentration of the reactant, you're going to double the rate. If you triple the concentration, you'll triple the rate. So whatever you do to the concentration, by whatever factor you multiply the concentration, you're going to multiply the rate by that same factor. That is very common. In fact, this is the type of reaction that our decay reactions were when we're talking about them in our nuclear unit. So again, recap, if it's a 0 superscript, 0 order, 0 effect. If the superscript is a 1, or the concentration simply has no superscript, it's an understood one, then if you do something to that the concentration of that reactant, you will do the same thing to the rate. Double it, triple it, whatever you do. Now, second order, if you have something that has a superscript of a 2 on it, these are common also, especially when you're dealing with reactions that involve gases. But if you double the concentration of the reactant in this case, you're going to quadruple the change. If you triple the concentration, whatever you do to the concentration, you change the rate by that factor squared. So if you triple the concentration, you're going to change the rate by a factor of 3 squared, or 9. If you quadruple the concentration, you're going to change the rate, increase the rate by a factor of 4 squared, or 16. So if a reactant is second order, changing the concentration is going to really affect the rate of that reaction. So 0 order means 0 effect for that particular reactant if you change it. First order, whatever you do to the reactant, you do the same thing to the rate. Second order, changing the concentration will square the change for the rate. So in a nutshell, if you have a reaction like this, or rate like this, like we just discussed, if M is 0, that means A would have this concentration of A, changing it would have no respect. Excuse me, it would have no respect. It would have no effect on the rate of the reaction. If M equals 1, it's first order with respect to A. And whatever you do to A would same effect on rate. If M equals 2, the reaction is second order with respect to A and to the concentration of A. Changing that concentration would square the change for the rate. And N, in this case, would have all of those same characteristics, but would be with respect to the concentration of B. So those are the orders that you're expected to know. And if you know the orders of the reactants that are in that particular reaction, adding those orders together would give you the overall order of the reaction. For instance, if M was 2 and N was 1, the overall order of the reaction would be 3 overall. And that's going to make a difference that we're going to see when we come down to looking at units for our decay constant. We'll see that in a little bit, but it is an important factor that you're going to have to determine whenever you're doing these problems. If no other information is given, assume that the units for rate are molarity per second. Remember, molarity is moles per liter, so moles per liter per second. Or, as most often you will see on AP materials, moles, liters to the -1, seconds to the -1. So those are our most common units for rate. You'll see it in meters, you'll see it in minutes also, sometimes in hours, but most often in seconds. So how are we going to do these problems? Generally, they will give us a table like this that has information about an experiment where they've done several different trials. And in those experiments, they have changed the concentrations of the reactants and seen what happens to the rate when they do that. So in this particular reaction, we see, or experiment, we see that they did 4 different trials, 4 different experiments, and they changed A and B. Each time there's a different concentration of A and B, and they calculated the rate. Now, the first thing it almost always asks you is, what is the general rate law or rate expression for the reaction? And in this particular case, it's going to be just what we've seen before. Remember, it always starts with rate equals K. And then we're going to put since it's dealing with concentration, we're going to put the values in brackets for the reactants and raise them to, by convention, the superscripts M and N for the general rate law or rate expression. The next thing we're going to want to be able to find is the differential rate law. The differential rate law is going to be found when we know what M and N are. There are 2 ways to do this: by inspection, looking at the table, and by calculation. During this particular video, we're going to look at inspection, and we'll do a different video to look at what the calculations would be. We can do this by inspection if we can find 2 experiments where they held one of the reactants constant and 2 different reactions when they held the other reactant constant. This one is a prime example. Experiments 1 and 2 held the concentration of A constant. Experiments 2 and 3 held the concentration of B constant, and that's what we want to look for. If they do that, then we can do this by inspection, which is easier. There is just kind of a template that I'm going to ask you to follow, because in order to do this by inspection, yes, many of us could just do it on our head, but AP won't allow just doing it in your head and throwing down a number for the order of a reactant. So this is the template that I want you to follow. It's going to have you list the experiments. That R sub CO is the reactant held constant, and the R sub CH is the reactant that is changed. You're going to see how the reactant was changed, see what that did to the rate, and based on that information, be able to figure out what the rate or what the order of that reaction is with respect to that particular reactant. So let's look at this and let's see if we can get this started here. In this particular case, I'm going to do the blue first, and when we look at the blue, we held A constant. You always want to go from the smaller to the bigger for the other reactants. So we're going from 0.1 to 0.3, and if you can't see it in your head, then you can simply divide, but this is changing by a factor of 3. It's being multiplied by 3, so it's tripling the concentration. Let's see what that does to the rate. If you'll notice the rate going the same way with the arrow, we went from 2 times 10 to the third to 6 times 10 to the third. That also multiplied by a factor of 3. It also tripled. So that's the information that we're going to put in when we start writing this. Okay, so look at your paper. I'm going to scroll this down, and you're going to want to see the table on your paper as you write this. We're going to just do exactly the same template format that we have that I mentioned before. And so we're simply going to write in experiments, and we use experiments 1 and 2, a concentration, and remember the concentration that stayed constant was A. The concentration of A was held constant, while the concentration of B was tripled. Okay, we're just filling this in with what's happening in the table. This caused, and there's no way to do this but to just memorize this template, and I expect you to do that. This caused the rate of the reaction to triple. Therefore, the order with respect to our changed variable, which was B, is. Now let's think about what that will be. If we tripled the concentration and that tripled the rate, what order does that? What order does the same thing to the rate that was done to the concentration? That's first order. So the order with respect to B is 1. I can make that look a little more like a 1. Okay, so that's looking at our concentration of B. So we just figured out up here that our B value, remember B is N, that N is equal to 1. So we just figured that out. Now we want to go back and figure out what M is equal to, and we're going to use a situation where B is held constant. And if you see, we've already marked that. B is held constant for reactions 2 and 3. So going from small to big on 2 and 3, we tripled A, so we multiplied A by 3. Let's look at what happened to our rate. Now, it may not be easy to see here, so if it's not, always take the big one divided by the little one. And if you do that in your calculator, you're going to get 9. This increased the rate by a factor of 9. And if you were paying attention earlier, this should already give you an idea of what's going to be true about the order of A, the order with respect to A. So let's write that up really quick. We're going to use the same exact template. but this time we're doing some different experiments. In experiments 2 and 3, the concentration of B was held constant. While the concentration of A was tripled. This caused the rate to, and there's no real word to reflect multiplying by 9. You can't say something like doubled or tripled. What would you say for something being multiplied by 9? So the way that we write this is to say that it caused the rate to increase by a factor of 9. Therefore, the order of the reaction of the order with respect to A is, and think about it, we multiplied the concentration by 3, which caused the rate to increase by 9. That's 3 squared. So when this happens, you know that the rate of A is going to be, or excuse me, that the order with respect to A is going to be 2. So we found out then that our superscript for M is 2. So what does that do as far as our rate law is concerned? Our differential rate law now is going to simply be to rewrite that rate, only this time we're actually going to put in the values, the order of the reactants. So A squared times B, and we could put a 1 as a superscript there, but usually AP will just leave it without any value there, and understood 1. Okay, so that's our first example. Let's go ahead and look at our next, went too far. Let's look at our next example. This case, there's something a little bit different. If you'll notice that instead of dealing with concentrations, we're dealing with pressure. We haven't done that before, so that's going to change a little bit how we write the rate laws and also how we word inspection. We can't talk about concentrations of these substances. We're going to have to talk about pressure. And we can't use brackets when we're writing the rate law because brackets indicates concentration, and we're not dealing with concentration. So the way we're going to write the general rate law is to say that rate is equal to K, and our two reactants are NO and H2, but we cannot put those in brackets. Okay, watch it. This is gonna trick you if you're not careful. The pressure of NO, sub NO, raised to the M, times the pressure of H2 raised to the N. It's just like the other rate law. The only difference is we're not using brackets, we're using parentheses, and we're talking about pressure, not concentration. So when we look at this, at writing this and following the template, we're going to change the template just a little bit. Instead of talking about these in terms of concentration, we're going to talk about them in terms of pressure. So let's look first if we can even do it by inspection. So we look at the initial pressure of NO, and we can see that reactions 1 and 3, experiments 1 and 3 held NO constant, and reactions 1 and 2 held H2 constant. So we're going to be looking at what happens from small to big, remember. What happens when we change H2? We doubled H2 there, went from 0.2 to 0.4. And what did we do to the rate in that same situation? We went from 0.01 to 0.02. We also doubled that. So that should give you an idea already of what's going on here. We know that H2 then is going to be, if we do the same thing to the reactant pressure as we do to the rate, that's going to be a rate order of 1. So that tells us what H2 is going to be. Now let's look at what's happening to NO. When we hold H2 constant over here in red, from small to big, we are going, oops, wrong color. We're going to be increasing the atmospheres, the pressure, by a factor of 2 again, so we're multiplying by 2 here. What happens to the rate in that same situation, going from reaction 2 to reaction 1? Looks like we are multiplying that by 4. We quadrupled it. So if we increase the pressure by 2, which increases the rate by 4, that's 2 squared, that means our order with respect to NO is 2. And our overall order, well, we'll talk about that later. So we already know what our order values are going to be by inspection, but we've got to write it up. AP will not accept that. So we have to write it in the form, in the template. The only difference is now we're using experiments 1 and 3. Sorry, I'm going to keep with my color scheme. In experiments 1 and 3, be careful, we can't use concentration. In experiments 1 and 3, the pressure of NO was held constant, while the pressure of H2 was doubled. This caused the rate to double. Therefore, the order with respect to H2 and really it should be pressure of H2 is 1. Similarly, in experiments 1 and 2, the pressure of H2 is held constant, while the pressure of NO was doubled. This caused the rate to quadruple, or you can say increase by a factor of 4. Therefore, the order with respect to NO It really should be pressure of NO. Let's fix that. And I really messed up my quadruple when I did that. So with respect to the pressure of NO is 2. So how am I going to write that differential rate law? Rate equals K. And again, this is a pressure situation. So pressure of NO squared times the pressure of H2 raised to the first, or simply left with an understood 1.